So far in your study of probability, you've looked at events that don't depend upon anything else. For example, you might ask yourself the chance that you land on tails 3 times if you're flipping a coin 3 times. Or you might ask yourself, on a given day, what's the chance that you wear a coat? So let's call the event that you wear a coat C. Okay, so that's what you've learned how to do, just like the probability of some event. But what if you were looking at something a little bit different? What about the probability that you wear a coat given that it's raining outside? So let's put that down. Let's see how we would write that. So we do the probability that you wear a coat. Then I'm going to draw this straight up and down line, which means given that it's raining. So maybe we'll call the event that it's raining R. Okay, so this is saying the probability that I wear a coat given that it's raining. In other words, I'm assuming that most likely the probability that I wear a coat given that it's raining is going to be higher than the probability that just on a given day that I wear a coat. Because if it's raining, clearly there's probably going to be a higher chance that I'm actually going to wear a coat on that day. So the way that we're going to think about this is the probability that I wear a coat given that it's raining is the probability that I wear a coat, and that upside down U represents an and. Probability that I wear a coat and it's raining. So a probability basically that event occurs over the general probability that it's simply raining. So in writing these two ideas out, I made probably a pretty reasonable assumption that there's going to be a higher chance that I wear a coat on a day that it rains versus just the probability that I wear a coat on any given day. But let's say for the sake of argument that I don't know that I don't know if there's a relationship or not. So this is what I would need to determine. So if I'm looking at the probability that I wear a coat, given that it's raining, I'm going to ask myself, is that the same as just the probability that I wear a coat? So if that's true, if this is true, then I call these two events independent of each other. In other words, the chance that I wear a coat given that it's raining is completely independent of just the chance that I wear a coat. The fact that it's raining doesn't in any way affect the probability that I wear a coat. If these are not equal, then my independent test fails. I assume that there must be some relationship between the fact that it's raining and the fact that I'm wearing a coat. There are some events that you intuitively know are independent of each other. For example, if I flip a coin and I land on heads, that is in no way going to affect the likelihood that I land on heads the next time I flip a coin. In other words, the second flip of the coin the outcome of that has nothing to do with the first flip of a coin. Or let's say that I flip a coin and then I draw a card from a deck of cards. The chance that I get an ace has nothing to do with the chance that I land on heads when I first flip that coin. So those two events would be completely independent of each other. So these ideas may seem kind of trivial, but in reality, independence tests can be very helpful. Maybe I'm a healthcare professional and I'm looking at statistics, and I want to know if the likelihood that a individual patient is a woman is in any way related to the likelihood that she will obtain a given disease. In other words, I could perform an independence test to see if the chance of getting a particular disease was in any way related to gender. So there are some pretty interesting independence tests out there, and they could be useful in that sense. So let's say I'm in a room full of 600 people, and I'm asking these folks what their favorite team is. So I have people from Durham, I have people from Raleigh, I have people from Chapel Hill. So speaking from a biased perspective, we have the most people in Durham. They tend to like Duke. We have people in Raleigh that tend to go for State, more so than the other two teams. And we have people in Chapel Hill who go for the obvious choice, UNC. So we're going to try and answer some math questions using this table. Specifically, we're going to think about conditional probability. So it's pretty easy for me to answer questions like, what's the probability that you're from Durham? So maybe I'll do the probability that you're from Durham. And that's simply equal to, well, there are 200 people from Durham, and there's 600 people overall, so I get 200 over 600. That reduces to 1/3, which is about 33%, 33.333%. Okay, I'm going to put a slash there to indicate that I'm definitely approximating. Okay, so, and then I could ask myself, well, what's the probability that you're a Duke fan? So I could look at that and I could do the probability that you're a Duke fan. And I see that there are 150 people and that are Duke fans, and there are 600 people overall, so then I just get 150 over 600. I come out to 1/4, or 25%. But those questions aren't too interesting. What if I wanted to ask, what's the chance that I am from Chapel Hill, given that I'm a Duke fan? Well, we'd have to look at the probability that we're from Chapel Hill, and we're Duke fans, over the probability that we're Duke fans. So let's think about that. The probability that I'm from, let's look at the top part first, the probability that I'm from Chapel Hill and I'm a Duke fan. So here's my Chapel Hill, and I know that there are 10 people from Chapel Hill who are Duke fans, and there are 600 people overall. So I'm going to do 10 over 600. So that's a fraction within a fraction. Now let's do the bottom part. Then what's just the general chance that I'm a Duke fan? So the chance that I'm a Duke fan is 150 over 600. Okay, I'm going to zoom out just a little bit. If I simplify this fraction, oops, sorry about that. If I simplify this fraction, the 600s go away, and I get 10 over 150, which is approximately 7%. So we know that the chance that I'm from Chapel Hill, given that I'm a Duke fan, is pretty small, because we wouldn't expect most Duke fans to be in Chapel Hill. But just in case we were unconvinced, we could do an independence test. So I'm going to ask myself, is the probability that I'm from Chapel Hill, given that I'm a Duke fan, equal to the probability that I'm from Chapel Hill? So I've already calculated the probability that I'm from Chapel Hill, given I'm a Duke fan, so that's 7%. My question is that equal to the probability that I'm from Chapel Hill? Well, there are 600 people in this room, and 160 of them are from Chapel Hill. So I'm looking at 160 over 600. Okay, so that's 160 over 600. And so if I do that math, 160 over 600, I get out approximately 27%. So it's very clear that the 7% chance I'm from Chapel Hill, given I'm from Duke, or given I'm a Duke fan, is not equal to just the general 27-ish% chance that I'm from Chapel Hill. So in this slide, we've calculated a conditional probability, and we've also thought about an independence test, how I can verify to someone, yeah, there's definitely a relationship between the chance that you're from Chapel Hill and the chance that you're a Duke fan. And it's exactly what we would expect. It's far more likely if I randomly select someone that they're from Chapel Hill than the likelihood that if I'm selecting someone from Chapel Hill, given that they're a Duke fan in this case. In the next slide, we're going to look at one more example. So in our last example, we're going to look at a situation where we're trying to think about gender, if someone's male or female, and the likelihood that they have a number of years of babysitting experience. So let's consider the fact, like, if you're male, for example, there's, out of a group of 100, there are 16 people that have no babysitting experience. There are 8 people that have 1 to 2 years of experience, and there are 8 males that have 2 or more years of experience. Whereas if we're looking at females, we have 30 people that have no experience, 17 people that have 1 to 2 years of experience, and 21 people that have 2 or more years of experience. So my question is there a relationship between, let's say, having 1 to 2 years of experience and gender? So let's try that. Let's look at an example of that. So let's try and find the probability that you have 1 to 2 years of experience, given that you're male. Okay, so that's going to be the probability that you have 1 to 2 years of experience and you're male, over the probability just that you're a male in this group. Okay, so the probability that you have 1 to 2 years of experience and you're male. So here's 1 to 2 years of experience. Here are all the males. So there are 8 people that have 1 to 2 years of experience and are males. So let's do that as 8 over 100. So that's the numerator of our bigger fraction. And then let's think about just the probability that you're male. Well, there are 32 people that are male, so I'm going to put that in here as 32 over 100. And if I put that into my calculator, I get out 25%. So let's see if that's equal to just the probability that you have 1 to 2 years of experience. Well, the probability that you have 1 to 2 years of experience, I know that there are 100 people in total, and if I take a look at my chart, there are 25 people that have 1 to 2 years of experience regardless of their gender, so that's going to be 25 over 100, and that's going to also be 25%. So what we can conclude is the probability that you have 1 to 2 years of experience, given that you're male, is equal to just the probability that you have 1 to 2 years of experience. So gender doesn't seem to matter in that regard. But let's look at another example that's really related to this one, but at the same time can bring up some interesting thoughts. So I'm going to take all this, I'm going to zoom out. Well, I thought I was going to zoom out. Perhaps I will pause and figure out how to zoom out. Okay, finally some success. Sorry about that. So let's calculate the probability that you're male given you have 1 to 2 years of experience. So you can see we're looking in the opposite direction that we were looking up here. So this is the probability that you have 1 to 2 years of experience given that you're male. This is the probability that you're male and have 1 to 2 years of experience. So that's going to be the probability that you're male. Oops, I should do the probability that you're male and you have 1 to 2 years of experience over the probability that you have 1 to 2 years of experience. Okay, so the probability that you have 1 to 2 years of experience and you're male is again 8 over 100, so we're getting the same thing that we are up here. So that's going to be 8 over 100. And all that's going to be over the probability of 1 to 2 years of experience. So the probability that you have 1 to 2 years of experience is 25 over 100. So let's put that in. 25 over 100. That reduces to 8 over 25. And out of that we get 32%. Okay, let's see if that's equal just to the probability that you're male. So the probability that you're male is 32 over 100. And that's equal to 32%. So we found, going in the other direction, that the probability that you're male, given you have 1 to 2 years of experience, is equal to the probability that you're male. But beyond that, there's a bigger, more abstract question that I think I'm going to put in green at the top right-hand corner of the screen. So the question was, we knew this. So we found the probability that you had 1 to 2 years of experience given that you were male was equal to the probability that you had 1 to 2 years of experience. Okay, in the same way, we also found that the probability that you were recorded as being male, given that you had 1 to 2 years of experience, was equal to the probability that you were male. So we can conclude that we can draw this relationship between having 1 to 2 years of experience and being male in either direction. We can do this, or we can do that. Both will work out. We don't have to do both. If we know one of these things, we also know the other. And our real solution within the context of the problem is there doesn't seem to be a relationship between gender and having 1 to 2 years of experience. Maybe there's a relationship between gender and having 2 or more years of experience or having no experience, but it doesn't seem like there's a relationship with 1 to 2 years of experience. Okay, So in this video, we've talked about independence tests, we've talked about conditional probability. At that point, we will conclude.